So in our first section here, we're going to go through a brief overview of segment routing, talk about what are some of the features for it, and then how does it differ from MPLS, which ultimately we'll see that segment routing is just another way of signaling MPLS. In the longer term, segment routing is going to be related to IP version 6, but we'll see in the current releases, the code versions that we're using, we're not going to have SR-IPv6 support. Okay, so like I mentioned, we'll talk about what is segment routing. Then how does segment routing work behind the scenes? We'll talk about some of the terms, try to get through the buzzword bingo and go through what are the marketing terms for segment routing and how do we map this to the actual functionality of the technology. And then finally, we'll take a look at how does LDP differ from segment routing and how could you essentially migrate between the two of them. Okay, so when you Google segment routing, typically this first website is going to come up, which is just segment-routing.net. This is essentially a link towards the standards. So segment routing is currently in IETF standardization. If you search like SR-IPv6 or SR-TE, you'll see the links to the RFCs that are related to that. But really what I wanted to talk about here is these two sentences or three sentences that they're describing here. It says segment routing provides complete control over the forwarding path, okay, so routing packets essentially, by combining simple network instructions. It does not require any additional protocol. Indeed, in some cases, it removes unnecessary protocols, simplifying your network. Specifically, the protocols that it is going to be removing is Label Distribution Protocol, or LDP, and potentially RSVP-TE, or Resource Reservation Protocol, when we're doing MPLS traffic engineering. Now, hopefully up to this point you are already familiar with MPLS because these examples that we're going to be looking at are a service provider core that has MPLS enabled, and then the application that's running on top of this is going to be the layer 3 VPN, where we're routing a protocol like OSPF BGP from the customer to the provider, and then we're trying to hop the traffic or essentially create an overlay network from the customer so that the devices in the core don't need that forwarding information. Okay, so the key point here is it says is that it does not require any additional protocols. Okay, so what does that mean then? If we don't need additional protocols, then what is segment routing doing? Okay, well, one is going to be simplification of MPLS traffic engineering. Because with TE, we no longer require a resource reservation protocol. This is assuming, though, that you're going to have some sort of SDN controller that has kind of an overall view of the network. What are the different segments or what are the labels that are being assigned? And then the controller can program towards the edge to say, I want you to route the traffic over the low latency path, or I want you to route the traffic over the guaranteed bandwidth path. So in terms of the forwarding of the traffic, when we capture it in the data plane, and we'll look at this on Wireshark, there's no difference between regular MPLS layer 3 VPNs and what we're doing here with segment routing. But the idea here is that you could have some sort of controller that is doing your traffic engineering calculation offline, as opposed to the online variations that we previously looked at, configuring the explicit paths, configuring the link and node protection. All those features are effectively built into segment routing, but a lot of this stuff is renamed as it goes with any of these new protocols, right? Okay, so like I mentioned, segment routing can remove protocols. So IGP is going to distribute the MPLS label bindings, and this is really going to be the main change. That normally in the core of the service provider, you're either running ISIS or you're running OSPF, and then you're running LDP in addition to those, where your IGP is creating the advertisements for the prefixes, and then LDP is doing the label binding on a one-to-one basis to those prefixes. So this is going to be our first big savings, is that since the IGP itself, so either OSPF or ISIS, has extensions to distribute the labels, this means that long-term we don't necessarily need to run LDP. However, in the meantime, assuming that the service provider network is already running LDP, we can do a brownfield migration, meaning we don't need to just turn LDP off everywhere, have an outage, and then turn on segment routing. There is a way to gracefully move between the two of those, and we'll talk about that a little bit later. Okay, the other key point, like I mentioned here, is that resource reservation protocol for traffic engineering is no longer needed for MPLS TE. Okay, also segment routing is going to be future-proof. because for right now it's using the MPLS data plane. So 99% of service providers are already running MPLS out there in order to do things like layer 2 VPN services or layer 3 VPN services. But for now, segment routing is still using that MPLS data plane. So when we talk about a segment, what we really mean is an MPLS label. Longer term, there is a standard for segment routing for IPv6, where the segments will be simply IPv6 addresses. So assuming that v6 is running natively in the core, then it means that we don't necessarily need MPLS at all going forward. Okay, in our particular versions of code that we're running in virtualization, both for iOS XR and for iOS XE, this feature is not yet added. So I'll come back at a later time and then add this once the code support is actually there. So we could talk about it in theory, but there's going to be no big difference in terms of functionality if we are encapsulating the IP packets over segments in MPLS, or if we're encapsulating them segments in IPv6. So we could have an IPv4 over IPv6 tunnel or an IPv6 over IPv6 tunnel. This is going to be for VPN traffic. So in other words, if your network is already built using regular MPLS and LDP, there's really no reason to change over to v6 everywhere in the core, because you can currently support 6 VPE, which is going to be an overlay network for your IP version 6 traffic. Okay, so how does segment routing specifically work? Okay, first thing we need to know is that we have this term that's called the Segment Routing Global Block, or the sRGB. So sRGB is just a fancy term for an allocation of labels. Okay, the label number starts at 16,000 and goes up to something like 23,999, somewhere around there. But the idea is that instead of having locally significant labels like we would with regular MPLS, we're going to advertise our loopback with a global label out of this global block. Okay, so in order to actually configure it, we run an IGP. Okay, so assuming we're already doing this, we're running either OSPF or ISIS. So next step is that we need to just turn on the extensions. Okay, so we enable the extensions, and then the IGP prefixes are going to be distributed just as normal. Okay, the difference here, though, is that when we advertise the loopback, we're going to create a manual binding between the loopback and a label value, and this label value is now going to be globally significant. So as we talked about in our service provider class, the MPLS data plane technically only needs the mapping to the loopback in order to get end-to-end connectivity, because when we look at this on the CLI, we'll see that the big important point of how MPLS connects together is the next hop value of BGP that we're advertising into our layer 3 VPN. So either VPN version 4 for IPv4 over MPLS VPNs, or VPN v6 for IPv6 over MPLS VPNs. So the key is that I take a customer prefix and I advertise it across the provider network to the other side, and when I do that, I set the BGP next hop to my loopback. This means from an MPLS labeling point of view, technically you only need the loopback to have a label binding in order to forward the traffic end to end. Okay, and that's essentially what's happening here, is that we're creating this global prefix segment ID, or what we call the prefix SID. And the prefix SID is basically just an MPLS label mapping, so a prefix to label mapping, just like LDP would create. The only difference is that we don't need LDP to do this anymore. Okay, it's going to be a function of OSPF or ISIS directly. So the idea here is to cut down on the load on the control plane and to cut down on the number of potential mistakes, just because we have a less number of protocols, right? So we could have a problem where you configure IGP on one interface, but you forget to configure LDP on top of it. Okay, we have an LDP and IGP synchronization issue. So if packets are being routed out that IP interface, but there's no labels, that's how we end up in a traffic black hole in the MPLS core. But in the case of segment routing, since IGP itself is distributing the labels, assuming that you have that mapping for the prefix SID towards your loopback, then there's essentially nothing else that we need to do in order to establish the MPLS data plane. Okay, specifically, like I mentioned, the segment routing global block, hey, look at that, I was actually correct. It's 16,000 to 23,999. So this is the default range that it uses. I'm not really 100% sure why you would need these many labels, because each router only gets one label now. The loopback is going to be manually programmed with a number out of this range. Additionally, it's recommended that they have the same range on all of the nodes. Not really 100% sure why you would change this, but this is one of the other potential issues you run into now, where previously with LDP, all of those labels were locally significant. In the case of segment routing, the loopback label becomes globally significant, so you simply need some sort of way to keep track of what are the numbers that you're assigning. Okay, like an Excel sheet or something like that says router 1 is node 16,001. Okay, we'll also see from the CLI there is a built-in mechanism from the protocol to detect if there's a conflict, but the ultimate result is that if both you and I are advertising the same label number, then there's going to be a problem when we go to forward traffic through the core. So in general, you just leave the sRGB default range what it is as default, but technically you could change this just like any other option, like any other nerd knob that you have. Okay, so how does LDP compare to segment routing? So in LDP, we advertise our prefixes in OSPF or ISIS. Then LDP starts running, and it takes each prefix that you're advertising, and it does a label binding to it. Now, the potential problem with this, though, is that we don't necessarily need the label numbers for the transit links. Okay, and let's take a look at our diagram here and try to visualize why this would be the case. Okay, so in our examples, we're mainly going to be testing connectivity end-to-end from router 6 to router 7, where these are two different layer 3 VPN sites. Okay, so we have site number 1, which is from router 4 and router 5 over to router 1 and XR1, and then we have site 2, which is going over to router 7. Okay, so router 6 is trying to send a packet, let's say the application itself. So we have the sender that is behind router 6, and then we have the application that is behind router 7. Okay, so 6, let's say for the sake of argument, we go to router 5. Router 5 sends a packet over to router 1. Router 1 now looks at what is the final destination that we're trying to reach. Okay, in this case, we have two different edge routers. We have XR3 as an edge router and router 3 as an edge router. So in our particular case here, we're using VPN version 4 route reflectors in the middle. So the packets are, the update, the BGP update about the prefixes are going to go to the reflectors, and then the reflectors are going to pass these on. Okay, let's say from router 1's point of view that it sees router 3 as the next hop. Okay, the key point here though is that the specific next hop value that BGP is advertising is going to be 3333, which is the loopback 0 interface of router 3. Okay, on the way back, router 1 is going to be advertising a route into BGP. It's going to take router 6's route, and it's going to be receiving it from router 5. It changes this into a VPN version 4 route, advertises it to the reflectors. Reflectors advertise it over to router 3. The key point, though, is that when we redistribute the route into BGP, the next hop is set to the local loopback. Now, in our final case here, we would see the label traffic going from 1 to 2 to 3, and then on the reverse path going the same direction. And we're transiting over these interfaces gig 2.12 and gig 2.23. Now, the issue is that when router 1 goes to advertise to router 2, or actually it would be router 2 advertising to router 3, it says, I have a prefix for this particular link. It's also going to be advertising, so the link is going to be advertised through IGP, but then the label value is going to be advertised by LDP by default. The end result of this is that for every possible link that we have in the service provider core, we're going to have an associated label for it. Where ultimately we don't necessarily need those, because if we're just transiting through the routers, where in other words, router 6 is never going to send a packet to the link between 2 and 3 directly, then it means that those are essentially wasted labels in the forwarding table. Okay, so the issue here is the labels for the transit links, they're not really required. Okay, they could be in there, but it's going to be a utilization issue in the control plane. Now in segment routing, we have a simple fix for this, simply because we have to manually map the prefixes. Now you could, in theory, manually map every prefix that you have on every interface, but at a minimum, the only thing that you really need is the loopback. Okay, the loopback, specifically when you advertise it as a prefix segment ID, or again what we call the prefix SID, it's called the node SID. Meaning that if I want to get to node router 1, I'm going to use segment ID 16001. If I want to get to node router 2, I'm going to use segment ID 16002. So the numbering convention in our case is going to be very basic. Router 1 is going to use index 1, router 2 is going to use index 2, and so on and so forth. But we do need to make sure that these are unique, because these label values now are globally significant to the entire service provider, as opposed to locally significant between me and my next top neighbor, as would be the case with LDP. Okay, so advertising only the loopback is going to reduce the number of global labels. This would be similar to LDP's configuration to say allocate global for host routes. This removes LDP's allocation of the transit links, but the key here is that this is not the default behavior. If you just turn OSPF on every single port and you turn LDP on every single port, then it's automatically going to advertise every prefix that you receive in OSPF with MPLS labels. Okay, the next term that we have is called the prefix SID versus the adjacency SID, or the prefix segment ID versus the adjacency segment ID. Okay, so segment routing IGP is going to advertise two different types of segments. So this is going to be for either OSPF or ISIS. It's going to be the same type of behavior, where the prefix segment IDs are globally significant, and the adjacency segment IDs, these are going to be locally significant. So if we go back to our diagram, let's say, for example, that router 1 is advertising the node SID of 16,001, and then on the link between router 1 and router 2, it is advertising on adjacency SID of 102. Okay, this value here is going to be locally significant. This value here, this is going to be globally significant. Okay, so why would you want to do this? Okay, main reason is going to be for traffic engineering. So if you're trying to do link protection and you want to say, I want this, if this link goes down, I want you to reroute the other way. Specifically, the way that's implemented in segment routing is to push the adjacency SID into the label stack. Now this assumes that you have some sort of device like an SDN controller, what's called the path computation element, that knows what are the adjacency SIDs, or what are the labels, because like I mentioned, those are locally significant. So if I'm the PE and you are 2 or more hops away from me, I'm not going to see any of your adjacency SIDs. I'm going to only see my neighbors that are locally connected. So this is kind of a mix between allowing detailed traffic engineering and trying to limit what the size of the label information base is, or the label forwarding information base, the LFIB. Okay, questions up to this point on the general overview of segment routing?